Hi, everybody. Today, John is going to tell us about general theorem and special extremal graph theory.
Okay, thank you. Let me begin by thanking the organizers for the invitation to speak, and thanks for everyone for coming to my talk. So yes, as the title says, I'll be speaking on a general theorem in spectral extremal graph theory, and everything I present in this talk is based on joint work that I did with Dear Desai and Mike Tate over the course of 2023. So I'll start with some basic definitions. If F is some family of graphs, then we call a graph G F-free if G has no subgraph isomorphic to some graph in this forbidden family. And then I'll speak often of the spectral radius of the graph. So just to make sure I'm clear, the spectral radius of G is the largest eigenvalue of the graph's adjacency matrix. So the two functions that we're interested in studying are the extremal number of F and the spectral extremal number of F. So the extremal number just means that you look at all n vertex graphs that are F-free and ask which one has the maximum number of edges. And the spectral extremal number is the same, except now we're maximizing the spectral radius instead of maximizing the number of edges. So these lowercase quantities will denote the maximum values themselves. Uppercase quantities will always denote the set of graphs that obtain the maximum. And the basic goal of this line of research is to find some conditions on the forbidden family which will allow us to describe a relation between the extremal graphs and the spectral extremal graphs when n is large enough. So typically you will find results in which one can say that the spectral extremal graphs are contained in the edge extremal graphs. And that's also the flavor of result that we were going for in this research. So I'll give some brief background on extremal graph theory to get oriented. So one of the fundamental results of extremal graph theory is the Erdős-Stone-Simonovich theorem, which says that for any graph F, the extremal number of F is this fraction of all possible edges, 1 minus 1 over the chromatic number of F minus 1, plus some small error term. So essentially, if F is non-bipartite, this means that the asymptotics of the extremal number are determined. And on the other hand, if F is bipartite, then we just end up with this small O of n squared from this theorem. So that tells us the extremal number. We also know a lot about the structure of the extremal graphs. So this result follows from the Erdős-Simonovich stability theorem. If F is any graph and R is the chromatic number of F minus 1, then any edge extremal graph can be obtained from the Taran graph by adding and deleting some small number of edges. In case you're unfamiliar, this TNR is a Taran graph, which is the complete R-partite graph where the sizes of the parts are as equal as possible. And this happens to be the edge extremal graph if one is forbidding a clique on R plus 1 vertices. So for the edge extremal functions, in the case of non-bipartite graphs, one could say that they're fairly well understood. What about the spectral extremal number? It turns out the same result that I just read for the edge extremal graphs also holds for the spectral extremal graphs. So this is a result due to Nikiforov. And again, it's exactly the same as the edge extremal result that I just read, except it applies to the spectral extremal graphs. So the edge extremal graphs and the spectral extremal graphs both have the same sort of general structural description, but are they actually the same, or do we have some containment relation between these two sets of graphs? So one recent result along these lines is due to Wang, Kong, and Xu, which says that if the extremal number is the number of edges in the Taran graph plus some bounded term, then every spectral extremal graph must also be edge extremal as long as n is large enough. So these types of results are the object of ongoing research. In fact, there's a recent preprint by Fong, Tate, and Zhai, which sort of generalizes this O of 1 term somewhat. But it's known, for example, that if you replace big O of 1 with a linear term here, or an arbitrary linear term, um, then this result is no longer true. Actually, that was shown by Deere, looking at the spectral extremal number of odd wheels. So there's some work left to be done to determine the sort of precise threshold where we can state a result like this. And in fact, I think some of the phenomena there will be similar to what happens in the bipartite case. Okay, so for the rest of the talk, we'll focus on forbidding bipartite graphs. And as I mentioned earlier, the Erdős-Stone-Simonovich theorem just gives us that the extremal number of a bipartite graph is small o of n squared. Now, we're not going to focus in general on most bipartite graphs, so this is just a very small overview of what's known. But if f is a bipartite graph, then the extremal number is less than n to the power of 2 minus some positive constant. And if f contains a cycle, then we can do better than linear. The extremal number will be at least n to the power of 1 plus some positive constant. But this third case is really what I want to focus on. If one forbids a non-trivial forest, then the extremal number is actually linear. So these are the types of graphs that we're interested in looking at. I should mention that there's one other way that one can obtain a linear Taran number, and that's by forbidding an infinite family of graphs. So for example, if you forbid all cycles, then the extremal graphs are just trees, which of course have a linear number of edges. Okay, so focusing in on this regime where we have a linear Taran number, I want to give a couple motivating examples illustrating the pattern that we were trying to formalize in our result. So first, let's say that we just forbid a path of length 6. Erdős and Galai showed that the edge extremal graphs for this forbidden subgraph are just obtained by taking a bunch of copies of the clique on 6 minus 1 vertices. However, the spectral extremal graphs are different. This is Nikiphorov's result. The spectral extremal graphs are just the join of a clique on 2 vertices with an independent set on the rest of the vertices. And maybe I can use this to give some intuition on how the spectral extremal function works. In the edge extremal case, anytime you add an edge to a graph, we're increasing the objective function by the same amount. It doesn't matter where you put the edge. But for the spectral extremal graph, if you sort of already have a vertex of high degree, then adding an edge incident to that vertex is worth more than adding an edge incident to only low degree vertices in general, which explains why we end up with these dominating vertices in the spectral extremal graphs. Of course, if one takes the spectral radius of like the disjoint union of these cliques, it doesn't matter how many cliques we have, the spectral radius will be the same. So it sort of makes sense that these families are disjoint in this case. On the other hand, there are cases where they can be the same. So if we forbid a linear forest, in this case, the union of 4 paths of length 3, then the edge extremal graphs are just the join of a clique on 3 vertices with a matching on the rest of the vertices. This was shown by Leditsky, Liu, and Palmer, who I believe characterized the edge extremal graphs for arbitrary linear forests. And Chen, Liu, and Zhang showed that the spectral extremal graphs are the same in this case. So sometimes they're the same, sometimes they're different. And initially our goal was to just find some conditions on the forbidden forest, which will allow us to conclude that these families are the same. But as we went into the details of the proof, it turned out that actually we could say something a little bit more general, where even, for example, in this first case, we can still determine the spectral extremal graphs given some combinatorial information. There's a way of sort of reducing the problem to edge extremal type problems, which I'll describe in a minute. Before I move on, I just want to set up some terminology. So the graphs that frequently show up as spectral extremal graphs often have like the join of a clique on the left-hand side with some relatively sparse graph on the right-hand side. So whenever I refer to left-hand side and right-hand side in this talk, I just mean the two parts of this complete, this graph which contains a complete bipartite graph where the size of the left-hand side is fixed. Okay, so our result is in fact not the first result of this type. In case it wasn't clear from the previous slide, just to clarify, this G plus H will always denote the join of two graphs G and H, where we just take the disjoint union of G and H and add an edge between every vertex of G and every vertex of H. So in a recent paper of Zhai, Yuan, and Yu, they showed that if the edge extremal number is the join of a clique and an independent set for n large enough, then the spectral extremal number is also obtained by the join of a clique and an independent set for n large enough. And actually, this result also holds if you add a single edge into the independent set on the right-hand side. They use this to determine the spectral extrema for certain star path forests. So our result is a generalization of this in a few directions. I need two more quick definitions before we state the result. So first is what I'm going to call this specialized extremal number. The idea is that we start with n vertices and we start with some graph G, and then we ask how many edges can we add to that graph without creating a copy of the graph F. I think this is not necessarily an interesting problem in its own right, but it's a useful device for stating the result. And then similarly, another kind of shorthand that we'll use is this kk comma infinity is a complete bipartite graph where one partite set, of course, has size k, and the other is countably infinite. And this is useful just because any graph F is contained in kk infinity if and only if it's contained in kk n minus k for n large enough. Okay, so now we're ready to state the result. So we have some forbidden family F, and there's a number of assumptions that it must satisfy. So first, the Taran number must be linear. Secondly, there must be, okay, so the Taran number being linear, in fact, implies that one of the forbidden graphs is bipartite. And here we sort of want to take the minimum value of k such that kk plus 1 comma infinity is not F free. So then kk infinity will be F free. So we know that kkn minus k is F free. And then we ask how many edges can you add to kkn minus k without creating a copy of any forbidden subgraph. And we assume that one of the graphs in this extremal family for that problem must be one of 6 forms. I only list 5 here because one of them has a weaker conclusion, so I did not want to clutter the screen. But the 6 forms that the graph can take, so it can either be a complete bipartite graph, kkn minus k, or B and C are the 2 graphs that we saw in the previous result. And then maybe instead of having an independent set on the right-hand side, we have some non-trivial graph on the right-hand side with a linear number of edges. So we'll call whatever graph appears in the right-hand side X. And it turns out that the behavior of the problem is different depending on whether the number of edges of X is at least 3/4 n or it's less than 3/4 n. So where this number 3/4 comes from will be clear in a minute. But yeah, you can see that if we have q at least 3/4, this parameter for the number of edges in X, then we require stronger assumptions in order to get the same conclusion. And what is the conclusion? So in cases A, B, and C, the spectral extremal graph is just whichever one of these cases we're in. It's the same graph H. And if we're in cases D or F, then we're able to say the following. So we start with the join of a clique and an independent set on the rest of the vertices, where the clique has order k. we ask how many edges can you add to that graph without creating a copy of your forbidden graph? And we can say that every spectral extremal graph must be some answer to that question. It must be one of the extremal graphs for that problem. Okay, so it's a fairly messy result, but it's motivated by the number of applications that we're able to get from this. Um, so I'll just go through one example that shows the flavor of how you can go about applying this result. So let's say we just have one forbidden graph, the star forest, so K1 D1 union K1 DJ, so the union of J stars. Of course, any forest has a linear Taran number, so the first assumption is satisfied. And then we want to know, okay, like what's the minimum K such that K plus one, sorry, K plus one comma infinity is not F free. And it turns out that we'll set K equal to J minus one because, of course, we can embed J like fixed stars in KK comma infinity, and we can't embed them in K J minus one comma infinity. Okay, so next we have to ask, so we sort of start with K comma infinity, but there may be some edges added in the left-hand side, and there may be some edges added in the right-hand side. So which sets of edges can you add while remaining F free? And in this case, there's a very nice description of these graphs. It turns out that Y join X is F free if and only if the maximum degree of the right-hand side is less than DJ. I think it's not too hard to see this. And so what that means is that the specialized extremal number starting from KKN minus K, in fact, this family is just every graph of the form KK join X, where X is DJ minus one regular, or perhaps almost DJ minus one regular, depending on the parity event. So we're in case F because it's possible that the DJ minus one over two could be larger than 3/4. But F is in fact satisfied because while the right-hand side is regular, so one of the assumptions in F is that all but a bounded number of the vertices have the same degree in these graphs. And secondly, if there's any vertex of degree dj, then we're no longer F-free. So again, it appears slightly messy, but for many natural forbidden families, the assumptions hold pretty easily. So every graph in the spectral extremal family must be of this KK join X form. And in fact, any one of these graphs has the same spectral radius, well, as long as you're DJ minus one regular instead of almost DJ minus one regular, it must have the same spectral radius, which can be shown using equitable partitions. And so at that point, we recover a result of Chen, Liu, and Zhang, that every spectral extremal graph for the star forest is also edge extremal. Okay, so here's a full list of applications that we're able to get from this result. If your forbidden family has one of the following forms. So I've separated this into finite families and infinite families where we can perhaps be forbidding cycles. And in this list, where there's a citation, that means that we recover an existing spectral extremal result. If there's no citation, then it appears that the spectral extremal result is new. Although there can be many other applications as well, here we've restricted ourselves to cases where the edge extremal number has actually been studied in the literature. But I think in many cases, it's actually easier to find the spectral extremal graphs than the edge extremal graphs. So I'll give a few notes on this. We have path forests, star forests. In certain small trees, we were able to make use of this literature on connected Taran numbers. Graph. Because if one knows the connected extremal graphs, then one also knows the answer to the extremal problems. in our theorem. So generally, if the edge extremal number or the connected extremal number of a graph is determined, then the types of problems that we need for our result should generally also follow from that. Okay, almost any tree. So this means that if you sample uniformly from all labeled trees on k vertices, then as k goes to infinity, the probability that we can apply our theorem to show that the spectral extremal graphs are complete bipartite goes to 1. So in some sense, almost every tree, for almost every tree, the spectral extremal graphs are eventually complete bipartite graphs, where the partite set is just obtained by taking like the smaller partite set of the tree minus 1. We'll give you the number of edges on the left-hand side. In fact, the spectral extremal graphs for any tree are known. There's this recent result of Fang, Lin, Xu, and Zhang, which appeared as we were finishing our paper. It seems that our result for almost any tree uses a sort of somewhat different method to find this fixed pendant structure that guarantees that we can apply our result. So this is hopefully sort of complementary to their result. Okay, I think at this point, I'll move on to say a little bit about the proof. So we have two main tools that we use. So the proof is rather elementary. So first, the eigenvector equations, these basically just come directly from the definition of the adjacency matrix, but it's useful to write them out explicitly. So if lambda is an eigenvalue of G with eigenvector X, then for any vertex U, lambda times XU is the sum over all the neighbors of XV. So some immediate consequences of this that are useful for our result, for example, if we select U to be the vertex with largest eigenweight, then this equation gives you a lower bound on the degree of U. Okay, and then if we multiply this equation by lambda, we get the second one. So lambda squared times XU will be the sum over all like walks of length 2 starting from U. So we use this very frequently. And then we also make very frequent use of the Rayleigh quotient. So lambda is also the maximum over all vectors of length 1 of the sum over all edges in the graph of the product of the eigenweights of the endpoint. So sort of a frequent way that this can be applied is, say, for example, if we knew that the eigenweights of all the vertices were the same, then maximizing this quantity is the same as maximizing the number of edges in the graph. So if we have very good estimates of the eigenweights, then we can say a lot from this equation. And this sort of indicates how sometimes the problems can be reduced to some kind of edge maximization problem. So I won't go into the details of the proof, but I'll give a very brief sketch using pictures. So if we assume that we have some spectral extremal graph, the first step is to partition the vertices into vertices of large eigenweight and vertices of small eigenweight using some carefully chosen cutoff. And after this, we can show that the number of vertices with large eigenweight can only be constantly many. Because if there were too many vertices of large eigenweight, then the spectral radius would be too large, and consequently the number of edges would be larger than our linear bound, which is assumed. After this point, we can show that if we pick a large vertex, its degree scales linearly with its eigenweight. So if its eigenweight is xv, then its degree will be almost xv times n. And after that, it turns out that their degrees are actually very close to n. So every vertex of large degree is almost dominating. Of course, I'm skipping over all the important details here. At this point, one can show that we have exactly k vertices of large eigenweight, because if there were more than k, we'd be able to find a k plus 1 comma infinity in the graph, which is not f-free. And if there were fewer than k, then the spectral radius would be too small. So we find exactly k vertices, each of which is almost dominating. That gives us that their mutual intersection cannot be too small. So we find a very large kk L, say, where L is very large. And there's a small proportion of vertices which are not in this large complete bipartite graph. Um, so if we call those exceptional vertices, then we can show that for any exceptional vertex, we can delete all of its edges and then make it adjacent to everything in the left-hand side without creating a copy of F. And this increases the Rayleigh quotient because at this point, the eigenweights of the vertices on the left-hand side is already so large that it compensates for all the edges that we deleted within the right-hand side. So in fact, there are no exceptional vertices, and we have a complete bipartite graph which spans our graph. At this point, in case A of the result were done, where we don't have any edges on the left-hand side, and in all the other cases, the edge extremal graphs have a clique on the left-hand side. And it's similar to show that we can have a clique here because we can delete many, many edges from the right-hand side and add a single edge on the left-hand side and still increase the eigenweight just because, sorry, still increase the Rayleigh quotient just because the eigenweights of the left-hand side vertices are so large. And then once we know that we have this structure in our graph, you can show that the eigenweights of all the vertices on the right-hand side are almost the same. And what I said earlier comes into effect, where essentially maximizing the Rayleigh quotient, like all that's left to determine is what edges are added in the right-hand side, and maximizing the number of edges is sort of equivalent to maximizing the Rayleigh quotient, again, because all the eigenweights are so close to each other. So it's the proof sort of splits into cases depending on which case we're in and our assumptions, but this is a broad outline of how it works. Okay. Returning to the statement of the theorem, I promised to explain this number 3/4. So why do we require additional assumptions when Q is at least 3/4? So we have a counterexample which shows that in fact, if we have only the weak assumptions, then the result is no longer true if we allow 3/4 n edges in the right-hand side. So we found the counterexample before we found the actual forbidden family. So in both cases, we want the edge or spectral extremal graphs to have two dominating vertices. And then in the rest of the vertices, it'll be some union of trees. In the edge extremal graphs, we take a union of a bunch of P4s with one P8. And in the spectral extremal graphs, we just take a union of these K13s. So this means that this graph has one more edge than this graph does. So this graph is actually not edge extremal. But the spectral radius of the graph on the right-hand side is larger. And a sort of intuitive reason why is that individually this star has a larger spectral radius than the path. So adding lots of copies of the star will increase the spectral radius enough to compensate for this single missing edge from the right-hand side. So the spectral radius on the right beats the one on the left by a very small amount. So what is the forbidden family F, which generates these two extremal families or extremal graphs? Well, I wasn't going for efficiency, but it turns out that if we forbid these several hundred graphs, it's pretty easy to show that the two graphs are the claimed extremal graphs. So we're sort of artificially forcing the problem to be easy. So of course, I doubt that this is like an optimal example, but I'm not sure how much it can be improved. So it would be interesting to see whether there's some counterexample that only consists of, for example, like one forbidden graph. And I'm really not sure whether that's the case. So maybe somehow we can say something stronger if the forbidden family is simple enough in some sense. Okay, so that's sort of the end of the spectral extremal part of our results. Um, the last big topic I want to talk about is we have the similar result for the A alpha adjacency matrix of a graph. So maybe instead of looking at the adjacency matrix, you want to look at this A alpha matrix, which is this convex combination of the diagonal degree matrix with the adjacency matrix. So if you plug in alpha equals 1/2, this just recovers half of the signless Laplacian matrix of your graph. And there are many results like maximizing the spectral radius of the signless Laplacian over F-free graphs. So if we can prove something for the A alpha matrix, then it also captures many existing results. And in recent years, there's been a large literature on spectral extremal problems for this A alpha matrix. So what we wanted to do was actually relate the SPEX alpha, which is defined analogously to the spectral extremal graphs, and the actual spectral extremal graphs. In other words, using alpha equals 0. So what assumptions on F can we use to say that these two problems are the same? And this result looks slightly different from the spectral extremal graphs. So here we do not necessarily need that the forbidden family has a linear to rand number. It may instead be the case that you're forbidding some bipartite graph F for which you can delete a vertex from F to obtain a forest. For example, like a cycle will satisfy this property. I think the intuitive reason why we can get away with slightly weaker assumptions here is that the presence of this diagonal degree matrix like even more strongly incentivizes having high degree vertices than does the adjacency matrix. So the importance of having like dominating vertices is just so large that it's easier to force the extremal graphs into that structure. So we assume that for n large enough, the spectral extremal graphs contain either the joint of a clique in an independent set or that graph with an extra edge in the right-hand side. And for any fixed alpha in 0 to 1, then for n large enough, the spectral extremal graphs or the alpha spectral extremal graphs are the same graph. And similarly to the spectral extremal case, we're able to get quite a few applications of this result. And again, if there's no citation, it seems that the alpha spectral result is new. So let me conclude with some open questions. So we found that our methods can be applied with like very slight modifications to many other extremal families. Sometimes there's only one or two lemmas that need to be modified in order to widen the range of applications that we can get. So maybe there's some more general theorem which would capture all the applications that we've listed and others. Some examples where we found this to be the case is with infinite forbidden families. So in the cases of our result where we have a non-trivial graph in the right-hand side, we need the additional assumption that the forbidden family is finite, or we may need it. But the only step in the proof in which we actually used the fact that it's finite is when we're getting rid of the exceptional vertices. And in every infinite family that we looked at, there was a workaround, basically using the structure of the forbidden family to get around that and apply the method. So it may be the case that we actually never need the assumption that F is finite. I don't have a guess whether this is the case. There are also some cases where the edge extremal graphs, or perhaps spectral extremal graphs, have a non-trivial graph in the left-hand side, meaning it's neither empty nor a clique. So maybe our methods can say something when this is the case. But it may be quite a bit trickier to deal with this example because then we sort of have to deal with the question of how many edges on the right-hand side are worth a single edge in the left-hand side. And assuming that our problems end up with the empty graph or a clique on the left-hand side sort of makes it a lot simpler to deal with. Also, okay, you may have noticed that the complete bipartite graph as the spectral extremal graph was missing from the A alpha result. So this is because if alpha is large enough, then it may be good to actually have fewer edges in the alpha spectral extremal graph. So for example, the alpha spectral radius of K1, comma, n minus 1 may be larger than the alpha spectral radius of K2, comma, n minus 2. So that's a counterexample which can show that if we're assuming that this complete bipartite graph is spectral extremal, that does not automatically imply that it's also alpha spectral extremal. But the method should go through for a certain range of alpha. So we're not sure exactly what the optimal range is and how it depends on the forbidden family. Some other open questions. It may be the case that the spectral extremal results hold even if the Taran number is more than linear. A reasonable guess might be that the exponent is strictly less than 3/2. I think we have examples where we have disjoint edge extremal and spectral extremal families if the exponent equals 3/2. And as I mentioned earlier, how much can our counterexample be simplified? So I think there's a lot of natural questions that you can ask sort of building on these results, and there's a lot of work that's left to be done. So with that, I will conclude.
Thank you so much for your talk. Are there any questions?
I have a quick question. So for John, and I don't know if Mike is still around, but so is there an example where this A alpha matrix can get you something that you cannot get with the A matrix or the Laplacian matrix, like some alpha that is not 0 or 1? Or maybe 1/2. I guess when alpha is 1/2, you get the signless Laplacian. So do you know an example where the A alpha eigenvalues can provide you information where the other eigenvalues cannot?
I don't know the answer to that question. I may just not be familiar with it, but yeah, I don't know. Sort of what we were trying to say here is that in some cases, like these two types of problems are the same. But going outside of like spectral extremal type results, I really don't know.
Okay, but your point here is that you can all these spectral extremal problems, you can sweep them all with all these matrices, not just with adjacency matrix or Laplace.
That's the idea.
Yeah. Okay. Thank you.